Hello everyone, welcome to Das Lake. This is our lecture number 2 on the 1000 question series, and which first we are dealing with the chapter heat transfer, and the topic for today is conduction, and this is part 2 of conduction, and previously we have uploaded the part 1. If you want, then you can go and check. So let's go to the first question. So this is our first question. With the temperature variation under steady heat conduction across a composite slab of two materials with thermal conductivity K1 and K2 is shown in figure, then which one of the following statements hold good? Okay, so in the options it has been mentioned about the relation between K1 and K2. Okay, so as this is series connection, so in series connection the heat that is traveling between one surface and two surface across 1 and 2 will be equal. Okay, Q1 will be equal to Q2. So what is Q1? Q1 by Fourier's law we can write it K1 dt by dx of 1, okay, is equal to K2 into dt by dx of 2. Yes or no? Yes. So as you can see in the figure, okay, here, okay, in the figure you can see that here the dt by dx of 1 and dt by dx of 2. Okay, we can judge that dt by dx of 1, okay, we can judge that dt by dx of 1 is greater than is smaller than dt by dx of 2 or not. Why I am telling this? Cause if you will see about the what is dt by dx, it is the slope of t in the x direction. Okay, so the slope of this line is less than the slope of this line. Yes or no? The slope of this line is less than the slope of this line. Yes or no? So if the slope of this line, okay, this line is less than the slope of this line, then dt by dx of 1 will be less than dt by dx of 2. Okay, if okay, now let's come to this expression. In this expression, okay, if dt by dx is less than this, then to equal both of the sides, K1 should be greater than K2 or not. Okay, then only equal to will be hold. If dt by, okay, for example, if dt by dx is 2 and dt by dx at 2 is, let's suppose, 3. Okay, to make this, okay, now if I'll apply 2k1 is equal to 3k3. Okay, so then this is for example only. Okay, so k1, if I'll write k1 in terms of k2, so this is k2 actually. Okay, if I'll write k1 in terms of k2, then that will be equal to k1 is equal to 1.5 times k2. So definitely K1 is greater than K2 or not. Okay, so our answer will be option A. Now let's go to the second question. Okay, similar question. In composite slab, the temperature at the interface, okay, this is the interface, at the interface between two materials is equal to the average of temperature of the two ends. Assuming steady one-dimensional heat conduction, which of the following statements is true about the respective conductivities? Okay, so in this question, first we need to draw the network diagram. Okay, the first resistance that we will encounter is the conductive resistance of slab 1. Okay, let's suppose this is 1 and this is 2. First resistance that we'll start from T1. Okay, this is T1, and the first resistance that will encounter is the conductive resistance of 1, and that will be equal to L by Ka, so 2B divided by K1 into A. Okay, the second, okay, now we are at point 2, that is the interface. Okay, this is the interface. So at the interface we have the temperature T2. Okay, so from here, when we will move forward, when the heat will move forward, it will encounter the resistance by the conductive resistance of the slab number 2. So the conductive resistance of slab 2. Okay, then the heat will reach at point number T2. Okay, it will reach at T2. So this is T2. Okay, so okay, let's suppose 1 second, as both of them we have written T2, let's make it interface Ti. Okay, let's make it Ti. Okay, so now okay, this is Ti, this is T2, and this is T1. Okay, so what will be the conductive resistance of slab 2? That will be L by Ka. L is B divided by K. K is K2 for the slab, and A. Okay, okay, now, so again, as I have said, when heat is traveling, okay, when heat is traveling from in a series, okay, so the in both of the slab, the heat will be same or not? Yes or no? Yes. So Q1 will be, okay, and the next phase, let me write. Okay, here the question is there. Q1 is equal to Q2. Q1 is equal to Q2 because both of them are in series. So how can I rate Q1? Q1 will be equal to, okay, Q1 will be equal to T1 minus Ti, okay, divided by 2B K1 A. Yes or no? Yes. Now, what is Q2? Q2 will be equal to Ti minus T2 divided by B by K2 A. Okay, so in the question, Ti is given. How? See, it has been written that assuming okay, the temperature at the interface between the two materials, okay, let me okay, the temperature at the interface between the two materials is equal to the average temperature of the two ends. Okay, so Ti is basically the average. Here I am writing Ti is basically the average of two ends, T1 plus T2 divided by 2. Okay, now and in the question we have to find out the relation between the conductivities. Okay, we'll find it out. So now, as I have said that this A and A will be cancelled out from both the sides, because it will go to the numerator and it will be cancelled out. Okay, the B and B will be also cancelled out. So now if I'll make this term, make K1 to the numerator, if I'll take the K1 to the numerator, it will happen like this: K1 by 2, okay, into T1 minus Ti, okay, is equal to K2 to the numerator, K2 Ti minus T2. Okay, so if I'll put the value of Ti, what it is okay, K1 by 2 outside, T1 minus Ti, Ti is T1 plus T2 divided by 2 is equal to K2 into, okay, T1 plus T2 divided by 2 minus T2. Okay, so what I get here, I will get K1 divided by 2, okay, 2T1 minus T1, okay, 2T1 minus T1, it is T1 plus T2 divided by 2. Okay, no, it is T1 minus T2 divided by 2. Okay, 2T1 minus T1 minus 2 minus minus, okay, minus T2. Okay, hope you all understand this. K2 in this side, okay, T1 T2 minus T2, T1 minus T2 divided by 2. Now, okay, T1 minus T2 divided by 2 in both of the sides, cancel out. Okay, so what is the final result? That is K1 is equal to 2K2. This is our final result. Okay, so option number D. Now let's move to the next question. A cold storage has 23 cm brick wall on the outside and 8 cm plastic foam on the inside. The inside and outside temperatures are minus 2 degrees Celsius and 22 degrees Celsius respectively. If the thermal conductivities of brick and foam are 0.98 and 0.02, and the inside and outside heat transfer coefficients are 29 and 12 respectively, then the rate of heat removal for a projected wall area of 90 meters square. Okay, so the first thing, let us draw the diagrams. Okay, I think this is perfect for foam. Okay, I have this pen now, I will draw it here only. Okay, let's suppose this is a foam of 8 cm thickness, and I need to draw a brick wall here. Okay, This is my brick wall. Okay, this is 25 mm thickness. Okay, okay, okay. So the foam is 8 mm thickness and this is in 25 mm thickness. This is foam and this is brick. Okay, Brazil, Russia, India, China, and K is for Kazakhstan. Okay, this is brick. So okay, the inside temperature is -2 degrees Celsius. This is -2 degrees Celsius and the outside is 22 degrees Celsius. Okay, okay. If the thermal conductivity of brick, K for brick is 0.98 and this is okay. It is given in the question, we'll directly use it. So okay, here there is some H value is given, H1 let's suppose, and here some else value is given, let's suppose H2, and this is K1 and K2. Okay, so what we need to find out, we need to find out the heat removal. Okay, the rate of heat removal. Okay, so okay, for these type of questions I have told you 1,000 times, first draw the network diagram. Okay, now let's do the network diagram for this. So here, okay, let me do it in the next page. So the first thing that I will encounter here is the convective resistance. Here, this convective resistance. So I'll start from temperature -2 degrees Celsius. So this is minus 2 degrees Celsius. I will encounter unconvective resistance. Okay, then I will enter, okay, I means heat, then heat will enter into this foam. Okay, so it will encounter, okay, this is, let's suppose, T1. Okay, and the heat will encounter a conductive resistance from the foam. Okay, and it will reach at the interface. Okay, so when it will reach at the interface, sorry, the brick wall will come. So the heat will encounter a conductive resistance from the brick wall. Okay, now heat is here. Okay, so the temperature, let's suppose this is T2. Okay, now heat will encounter a convective resistance. Okay, let us draw, okay, this color, convective resistance, and it is finally at the outside, that is 22 degree Celsius. Okay, so okay, I need to find out the heat removal rate. Okay, the heat removal rate will be equal for all or not? The Q, the same Q, because all of them are in series. But I don't know T1, I don't know Ti, I don't know T2. Okay, I don't know any of the temperature. Okay, I know the temperature of these two nodes. Okay, these nodes. this and this. I know the temperature of these two nodes. Okay, to find out the heat transfer, you need to know the temperature of two nodes. I know the temperature of two nodes. Okay, then I can write the heat transfer Q is equal to, okay, first this is, let's for -2 and -22. So this is the temperature. Then I have to write the resistance, okay, R. So in the R, first this is first resistance, this is the second resistance, this is the third resistance, this is the fourth resistance. It is R total. Okay, I need to write all of them, all of the resistances, the sum of all of the resistances. So now I will write one by one. Okay, first the convective resistance. Okay, this is the convective R convective 1. This R convective 1 will be equal to 1 divided by HA. Okay, H is given. Okay, this side H is, okay, inside and outside. Inside is 29 H and outside is 12. So 29 into A is given, that is 90 meters square into 90. Okay, now this is the conductive resistance 1. This is L by K. L is 8 mm, so 0.008 divided by K. K of foam. K of foam is okay, thermal conductivity of brick and foam 0.002. 0.002 into A is 90. Okay, now this is R conductive 2, that is a brick, that is again L by K. L is 25, K is 0.98, A is 90. L is 25, 0.025 meter. Okay, that is given in the mm. K is what is K? K is 0.98, A is 90. Okay, this one is the convective R convective 2. Again 1 by HA, 1 divided by HA. H is 12 into 90. Yes, so I need to add all of them to get the total resistance. First add all of them. Okay, R total, okay, between -2 to 22 will be equal to 0.0406. This is the R total. So the Q will be, okay, the Q will be -2 -22 divided by 0.0406. okay, and this is equal to -1083.74 watt. Okay, so why this is in minus? Because heat is traveling from here to here. Okay, we have calculated heat is traveling from here to here. We have assumed that his direction, the direction of heat transfer is from here to here, but actually this is at low temperature and this is at high temperature. In actual practice, heat will transfer from here to here. Okay, high temperature to low temperature. So this is the answer. Now let's move to the next question. Okay, this is a wonderful question. Heat flows through a composite slab as shown below. The depth of the slab is 1 meter. Okay, the K values are given. The overall thermal resistance in kilowatt. Okay, this is a thermal resistance. We have to find out the overall thermal resistance. So first, let us draw the network diagram. Okay, first I will start from here, this position. Okay, I'll start from this position. First thing that will encounter is a conductive resistance from this. Okay, and this is equal to 0.5 L by Ka. 0.5 by Ka. K is 0.002. Okay, into A. Let's suppose that is A. The area is not given, so I'll say A. Okay, let's suppose width is W and the length is given, that is 1. Okay. I can do it. Now I am at this position. Okay, I am at this junction. With this, okay, Q amount of heat has come from here. Q amount of heat has come from here. Now the heat will be divided into two parts. Q amount of heat has come here. Some part of it will go to Q1 and some part, Q2. Let's suppose this is Q2 and some part of it is Q3. Okay, as these are in parallel connection, okay, these two and 3 are in parallel connection. 2 and 3 are in parallel connection. So the heat will be divided between them, and the initial temperature, the initial temperature and the final temperature will be same. Okay, so I will see. Okay, parallel connection. From here, two nodes will come. This junction. Okay, let this be A. Okay, this junction be K. And from here, one resistance, conductive resistance will be there. And the below part, there will also be one conductive. Okay, from here, two resistance will become. Okay, the upper part is L by Ka again. So L will be, for the upper part, L will be L by K. So 0.25, okay, because this length is 0.25 divided by K. K2 is 0.1 into A. A is W into 0.5, because the length is here 0.5 only. Okay, now the below part, again the same formula, that is L by Ka. L is same, 0.25, okay, divided by K. K is 0.004 into A. A is W. Let's suppose the width is W and length, the thickness, that is 0.5. Okay, so this is our basically the network diagram. From here we need to find out the the total resistance. Okay, so first let's suppose assume W is equal to 1. question I think the depth of slab is 1 meter. Okay, it is given. The depth of slab is 1 meter, it is given, so we don't need to assume, it is given. So W is 1 meter. Okay, now let us first calculate these values so that it will help us. Okay, 0.5 divided by 0.002. So 0.5 divided by 0.002, it will be 250. Now 0.25 divided by 0.1 into 0.5. Okay, this is equal to 5, and this value, that is 0.25 divided by 0.004 into 0.5. Okay, this is 125. This is 125. Okay, so we need to find out the resistance, total resistance. Okay, first we'll convert these two resistance into a single resistance. Okay, these two resistance into a single resistance, okay. So my new network diagram will be equal to, okay, first let us find out the value. Okay, first see, my new network diagram will look like this. Okay, this is 250, and from here the resultant of these two will be some value. And now I need to find out this value. Let's suppose that is R. Okay, so what is R? R will be equal to, R will be equal to, okay, 5 into 125 divided by 5 plus 125, cause in series 1 by R is equal to 1 by R1 plus 1 by R2. Okay, so by simplification you will get R1 R2 by R1 plus R2. So 5 plus 125. Okay, so it is something around 4.807. so my R is 4.807. now these two resistance are in series, so I just need to add them up. So R total will be equal to 254.27. okay, I think I have made a mistake here. Okay, what is the mistake? Okay, see here, it is the K1 is 0.02, but I have taken 0.002. That's why a mistake has come, but I will rectify it for you. So it is 0.5 divided by 0.02. okay, it will be equal to 25, not, okay, this is 25, and one more mistake is this is 0.04. okay, so this will be equal to 12.5. okay, this will be equal to 12.5, and so this is 12.5 and this is 12.5. okay, so 5 into 12.5 divided by 5 plus 12.5. okay, this is 3.57. okay, this is 3.57 and this is 25. so it will be, total will be something around 28.57. okay, it is, so 28.57 is the, sorry for my mistake. Now let's move to the next question. Okay, question reads like, with an increase in the thickness of insulation around a circular pipe, heat loss to surrounding due to convection increases while heat due to conduction decreases. Convection decreases while due to conduction increases. Convection and conduction decreases. Convection and conduction increases. Okay, the answer will be the heat loss due to convection will increase, but heat loss due to conduction will decrease. Why? Because for suppose this is what is that? Yes, this one. So okay, let me change the color a bit. Okay, so let's suppose this is one pipe is okay. If now I will apply some some what you mean, you know, insulation to it. Okay, if I'll apply some insulation to it, then what will happen? See, if I'll apply some insulation, then the material will increase. Okay, the insulation material will increase or not. So the radius will increase. Okay, the total radius that will increase. So what will happen? The conductive resistance will increase. So heat transfer due to conduction will decrease. Okay, but if you see that the surface area, okay, the surface area has increased. As A is increased, so as A surface area is increased, so Q convection will also increase. Okay, from this phenomena only the the critical radius of insulation comes. Okay, now let's move to the next question. The answer will be A. So we're talking about the critical radius of insulation. Now this is a question of, up to critical radius of insulation, convection heat loss will be less than conduction heat loss. Heat flux will decrease, added insulation will increase heat loss, added insulation will decrease heat loss. Okay, the answer will be, up to critical radius of insulation, added insulation will increase the heat flux, because up to critical radius of insulation, the the Q convection, increase in Q convection, okay, the increase in Q convection will dominate over the increase in decrease or decrease of Q conduction. Okay, so this one will dominate over Q conduction up to critical radius of insulation. After that the decrease in Q conduction will start dominating, and the heat loss will decrease. But up to critical radius of insulation, the insulation will increase the heat loss. Okay, so now let's move to the next question. So the question reads like, in a foam insulation if a foam insulation is added to a 4 cm outer diameter pipe as shown in figure, the critical radius of insulation. Okay, one thing that you need to remember or understand, whatever, the critical radius of insulation do not depend on pipe dia. Okay, critical radius of insulation do not depend on pipe dia. Okay, so now or the and pipe conductivity. Critical radius of insulation do not at all do not depend on pipe dia or pipe conductivity. So this this data 4 cm data of no use, and the pipe conductivity is of no use in finding the critical radius of insulation. Okay, so what is the critical radius of insulation? Remember the formula, that is for a pipe okay, the critical radius of insulation will be equal to K of insulation divided by H outside. Okay, and similarly for a sphere the critical radius of insulation is 2 times. Okay, let me do okay, 2 times K insulation, okay, divided by H outside. Okay, okay, the insulation that will apply here, the K will be of that. So the critical radius of insulation for, okay, this is not a sphere, okay, this is a cross-sectional view. It is already mentioned that this is a pipe. Okay, so don't apply that don't apply this formula, apply this formula K in, because this is a pipe, K insulation by H outside. So K insulation is given, that is 0.1 and divided by H naught, that is 2. So 0.1 divided by 2 meter. Okay, that will be 0.05 meter. Okay, this is so. Okay, one thing you need to see here, mark here, it has been asked in cm, so it is 5 cm. Don't give answer in meter, because it is a numerical data type question. If you will put 0.05, it will be wrong. Okay, now let's move to the next question. So okay, a 10 mm diameter electrical conductor is covered by an insulation of 2 mm thickness. The conductivity of the insulation is 0.08 and the convection coefficient at the insulation surface is 10 watt per meter square Kelvin. Addition further insulation of the same material will be, okay, option will read later. So first and foremost thing, okay, so electrical conductor. What is electrical conductor? Okay, what is electrical conductor? Okay, let's suppose this is wire only. Okay, so wire, you can assume that it is a what, pipe or not. So what is the critical radius of insulation of a pipe? That is RC is equal to K insulation by H. That is K is what is K is 0.08. I will not see the two diameter now. Okay, first when I'll calculating the critical radius of insulation, the diameter has no role in it, so don't see that at all now. K insulation by H is 0.10. H is 10. So my critical radius of insulation will be 0.08 divided by 10, 0.008, okay, meter, and which is equal to 8 mm. So my pipe diameter is 10 mm. Okay, so this, let me change the color. Okay, let me do it here. My pipe diameter is 10 mm. Okay, my critical radius of insulation, okay, if I'll apply my critical radius of insulation, then okay, the maximum radius of insulation, okay, that is what, 8 mm. So this is 8 mm. What is the thickness of insulation? That is, now thickness is 2 mm. Okay, the insulation thickness is 2 mm. So okay, the if 10 mm is the dia is 10 mm of my pipe. So what is the radius of my pipe? Okay, the radius of my pipe is what, 5 mm. Okay, let me draw the, so that you will understand it well. Okay, let us draw it here. One second. This is my pipe. Okay, now I will apply my, okay, well, this is my critical radius of insulation. And now what is my current insulation? My current insulation is up to this. How? Let's see it here. So my radius of pipe is now 5 mm. Okay, I have applied a insulation of thickness of 2 mm. So this thickness is 2 mm. So this radius is now 7 mm. My critical radius of insulation is what, 8 mm. So my current insulation, okay, my current insulation is less than my critical radius of insulation. My current insulation is less than my critical radius of insulation. This one thing I need to understand. Okay, now addition of further insulation. Okay, addition of further insulation. If I further insulate it, then what will happen? If I further insulate it, then the heat transfer, okay, my heat transfer is, let's suppose it is now here. Let's suppose it is now here. If I'll further insulate it, it will increase, then it will decrease. So this is my R critical, and this is my current insulation. So okay, first it will increase, then increase heat loss to a maximum, then decreases heat loss. This is my answer. Okay, because it is this is heat loss, so this is outer radius. So first heat loss will increase, then it will decrease. Okay, first heat loss will increase, then it will decrease. First it will increase, then it will decrease. Currently I am here, I will increase up to critical radius of insulation, and it will decrease. Okay, now let's move to the next question. Okay, so the value of thermal conductivity of thermal insulation applied to a hollow vessel, okay, hollow spherical vessel containing very hot material in 0.5 5. Okay, the value of thermal conductivity of thermal insulation. Okay, the K of insulation is given, that is 0.5. okay, the convective heat transfer coefficient at the outer surface, okay, that is 10. Okay, H outer is 10. So what we need to find out? The critical radius of insulation. Okay, here I have told you what is the critical radius of insulation for a sphere, that is 2k insulation into S naught. Okay, so my RC for a sphere is 2 times k insulation, that is 0.5 divided by 10. Okay, this is 0.1 meter. So this is all. Thank you. This was the last question. Okay, with this the conduction is completed. From today from tomorrow we'll do the question on convection. Okay, if you have liked this video, then please subscribe the channel, and please share the channel or video with your friends, okay, who wants to do some good questions. Okay, thank you.